Chapter 5 is stereochemistry. Stereochemistry is something that we've already been learning about, which is about three-dimensionality, about wedges, hashes, about it not being in the same plane. So usually we're talking about sp3 configurations where we have a tetrahedral type shape. Knowing where it's located and having an idea of one element or attachment and its relationship to another will help us decide and determine how many of them will interact with each other. So the big first term that we're going to learn about today is a thing called chirality. Chirality is basically a fancy way or a different kind of word of saying handedness. So you like right-handedness or left-handedness when you're talking about a compound. And I will try to help explain what that means. So if you are chiral, what you're really doing is you cannot be superimposed, and I have some images on the next page on this. You cannot be superimposed on its mirror image. You are not the exact same. So you are unique. And I will explain that in a minute. If you are achiral, then that is the same as its mirror image. Okay? And that has some differences with that. And then that leads us into a final term that we've already learned a little bit about, but we didn't really do a lot with it, is something called an enantiomer. In an enantiomer, you have mirror images, but they are different and are not superimposable. Okay? So when you have a mirror image, if you put them on top of each other, they are not the same. Okay, so we will kind of talk about that. But note, enantiomers involves a relationship between two structures. You always have to have two different structures. Okay, chiral can actually be talking about a single molecule. So if I say enantiomer, I have to compare it to something else. I can talk about any one object or molecule as chiral or achiral. Okay, so when we're drawing mirrors and enantiomers, okay? The key to this is we can exchange any two attachments, and it inverts the stereochemistry and produces a mirror image. So if we're able to do that, then we are able to make an enantiomer, and I'm going to show you this right below right now. Okay, so if we start, don't worry about these letters, these S's and R's. We'll talk about that in our next lesson. But if we are discussing this compound right here, okay? So I have a hydroxide that's coming at me, I have a hydrogen that's going away from me, and then it's on this butane zigzag shape, okay? What happens is if I flip, let's see, which one do we want to do first? Let's say I flip this one. So if I flip the H and the OH, oh sorry, no, actually I'm flipping the butane, okay? I'm flipping the butane here. So when I say two things, what I have is I have 1, 2, 3, 4 coming off of my carbon. Okay, so what I did on this one is I flipped how my butane was in orientation to my carbon, or you could almost think of it as the methyl here and the ethyl here. Okay, so I flipped that. All right, so now these in theory are called enantiomers. They are mirror images of each other. I'll show you some more later, but this is probably the easiest one to do. And you're flipping the OH and the H. Okay? So we flipped the wedge and the hash. Okay? That becomes a mirror. If you look at these two, they are mirror images of each other. You may not feel like it right now, but if I turn this around, then this whole thing, and you put it up next to each other, they are mirrors. Here, I should have written this before, I flipped maybe the front and the back. And that again becomes a mirror. The last one's probably the most odd, is that instead of having it either flipping the bottom or flipping the top, what if I flip the side? So I actually rotate it. Again, having a model in front of you probably is a little easier. if I flip that and I flip the side, I make a mirror. Okay, to me, by far, most convenient. So we'll talk about this more, but you just got to keep kind of remembering this initial example. That is, if I flip any one, there's 4 constituents off of this. If I flip 2 of them with each other, I'm making it an enantiomer. That's the only thing I need you to kind of get from this right now. So a chiral carbon, or what we sometimes call a stereocenter carbon, it is when, and I cannot emphasize this enough, is any tetrahedral atom has 4 different attached carbon groups. Not carbon groups, just groups. It makes it a chiral carbon. And that's what we need to be finding, and we're going to be doing that in a second. So 4 different attachments. It's a chiral carbon. So what do I mean by 4 different attachments? Let me show you on this one again. If I have a C right here, okay, I'm actually going to draw it out here once. This C has an H. It has a CH3. It basically has a CH2, CH3, and it has an OH. Those are 4 different attachments to my carbon. That makes it unique, and it has a lot of special properties in a reaction that we need to look at. Okay? So this then says recognizing chiral carbons. So I'm just going to briefly talk about it, but I'd rather be doing. So I will discuss this later with it being achiral, 0 chiral carbons. You know what? We'll move on from this right now. Sorry, I'm distracted. There's a ton of people making noises outside my door, and it's throwing me off. So what do I mean about handedness? So if I have this hand right here, and I'm talking about something that's chiral, okay, it means that if I have a left hand and a right hand, even though in a mirror they may look the same, right? As I'm looking at it, my thumb's on the proper side, my pinky's lined up, but when I put them together, they cannot be superimposed. Okay? That makes it special. That makes this hand unique and this hand unique. If you can impose them, they are not special. And what they are considered then is achiral. So I have this flask, and it's a mirror of this flask. But the problem is, I put it on top of each other, and it's the same. So it is not special. This mirror, or this flask is not special over that flask. But this hand is special to that hand. So looking at this, they might look the same. When I have a mirror here, look at that. This is going away from me. This is coming at me. This is going away from me. But it's trying to show the same idea with the hands. If I would turn and put this in front of the other one, it would be totally opposite, right? The thumbs are on the wrong side. These would be on this side. This would be on this side when I put it on top of each other. So these are actually unique compounds. And the reason why I know is there is 4 different compounds around my carbon. So that is going to be a unique structure. So the difference is in this one. If I look, mirror image. The problem is I have 3 hydrogens, okay? So my carbon does not have 4 different attachments. Okay, because of that, it's achiral. So these are not enantiomers. Right, let's take a look at a couple other examples. So what we do in AP chemistry, or in organic chemistry, is that we put a little star, little asterisk, next to a carbon if we are saying that it is chiral. And the reason why is that I have my bromine here. So there's my bromines. I'm going to do this in 4 different colors. Here's my hydrogen. Here's my chlorine. And here's my fluorine. Although mirror images, no matter how I rotate this, so if I rotate this a little bit, I'm going to take this one and I'm going to rotate it a little bit here. And I'm going to look at it on this side. check it out. It is not, I can't place this one on top of anything. I can't. Now, I could if I move something around. If I move these two, I could make it into that one. And then that's an enantiomer of each other. But right now, because they're special, I can't actually superimpose them. So these are considered chiral. 4 different attachments around the center atom. Here, unfortunately, I have 2 of the same. So they have 3 different attachments. So because of that, this is not chiral. So we say it, instead of not chiral, we say achiral. And the reason why is that I can, although this looks like they might be different, all I got to do is rotate this around, and this becomes this one again, which is exactly the same. So it is not different. They are not special. So right now what I want to do is I want to look at a few of these and talk about which ones are different. And it's as simple as saying there's 4 different ones. So it has to have 2 rules. 1, it does have to have 4 attachments, so it has to be an sp3. And 2, it has to have 4 different attachments. So because of that, I put a little star. That one's chiral. Chiral. All right? So take a moment, look through these. Which ones are chiral, which ones aren't? I will talk about it. The bottom ones, okay. I already give the answers away. Super! I didn't notice that. So let's talk about why each one's the way they are. I have 2 here, so because of that are the same, it's achiral. Here, I have a meth, I have an eth, and I have a prop. I know that you might look at this and go, well, it's a carbon, and a carbon. They're different though, because they're longer branches or they're shorter branches. So because of that, little star, chiral. And finally, you go, well, these are all different. Yes, they are. The problem is, this is an sp2. Because of that, if I have a mirror and I drew this out, even though I drew it like this is all in a plane, and it's a mirror image, I can just flip this around, right? And it would look like this again. So that's why this one is achiral. All right, so let's take a look at a little more realistic looking problems. So we're going to classify each one as chiral or achiral, and then we'll move on from there. So right away, if you are struggling with this, like any atoms on here. So for example, I have 3 H's, okay? I have an H, and 3 H's. So what I need you to understand right now is that these are all the same, so this can't be chiral carbon. These are all the same, can't be a chiral carbon, and this has 1, 2, 3 clouds. These are sp2s. So because of that, none of them can be. So there's nothing in this one. There's nothing in it. This is 1, 2, 3, 1, 2, 1, 2, 1, 2, 3. What am I doing? I'm doing H's. The minute that I have 2 of the same or 3 of the same, it can't be chiral. So if my carbon right here, I'm looking at it, I have 2 maybe different endings here, but the H's are exactly the same. So that's not chiral. Oh, this looks like the problem that we just did a second ago. So this carbon right here has 3 or 4 different attachments. So this one is chiral. So what I do, I put a little asterisk next to it. Okay. This one, cyclical compound. So here is cyclohexane, pentane, cyclopentane. So I'm looking at this carbon right here. So here it is. I have a bromine, I have a hydrogen. All right, but now if you're like, oh, carbon, carbon. With a cyclo, if the path is different, then it's different. So here I go CH2, CH2. Here is another CH2. Here's a carbon with a bromine on it and an H. This is different than this. So this is chiral. And if you can't tell, it's going to be the same thing. I come here and I run into bromine. Here, I'm not there yet. So it's not the same. So here I have two chiral carbons. Okay. So I'm going to talk about that for a second. Yes, this is chiral for the carbon, but when you have two of them, let's go back to the original page. If you have two chiral carbons, it may be chiral or achiral. So this gets confusing. If no plane of symmetry, it's chiral. So no plane, it's chiral. But if there's a plane of symmetry, it's achiral, because what it will do is it will balance itself out. It will cancel it out, basically. So if I look at this right here, is this side the same as this side? And I say yes. So there's a plane of symmetry. So what we call that, shoot, I passed that up on the notes, I'm so sorry. It's a big word. It's called meso. This is a meso. A meso is when you have two chiral carbons, but you have a plane of symmetry. So what I would say is this becomes meso. Because of that, it's actually achiral. Keep going through the rest of these. Again, check this out. So I have a Br and an H, and then the route, boom, boom. So that is chiral, and that is chiral. But now, plane of symmetry, these are not in the same plane. These are not in the same plane. So this is considered chiral. Okay? Because they're not in a plane of symmetry. Not in a plane. All right, is this carbon chiral? You can get confused by all of this stuff going on, but here's what I see. Two H's. Not chiral. Achiral. And then finally, same idea. These are going to be chiral. Plane of symmetry. Nope. Br and Cl are different. So this is going to be chiral. All right. You're almost through this. So let's just do a couple more things. What is the relationship between the following pairs of structures? Are they the same or are they enantiomers? Okay, same or an enantiomer. So the key to this, you guys, is does this flip? So first, you got to have chiral carbons. So I have 1, 2, 3, 4 differences. 1, 2, 3, 4. There's 4 different things here, so these are both chiral carbons. So the thing is, they are the same if nothing has changed. But in this case, although the butane is the same, I have hydrogen and hydroxide there, and it appears that this is flipped. So I did a hash wedge flip. So this is how we classify an enantiomer. Okay? They are mirror images. Now, if you're like, how is that a mirror image? Because if I put this over here and I put it in the same context, it will look the same. Okay? It will be the same. So if I now take this one over here, I'll do this one time, and I take this shape right here, and I actually draw it, so now it's the other way. So now I flip it. If I flip this actual whole structure, the whole thing together, oops, I did it wrong. Is that this is now going to be coming at me, and this is going to be going away from me. Check it out. I actually just rotate this whole thing, not just this, all of it. I rotate the whole thing. My H is going away, my OH is coming at me. Now this looks like a mirror image, but they're not the same. If I place this on top of it, I can't superimpose it. If I place this on top of that, it's not the same. It's the same mirror image, but they're not the same compound. So that's why they're considered enantiomers. They're mirror images of each other. They cannot be superimposed on top of each other. So this one again, these are chiral carbons because there's 4 different attachments onto them. So again, I look at it, what has happened? Well, this time I flipped just the bottom two, right? Flip the bottom two. So we've learned if you move two parts of the chiral carbon, then it's an enantiomer. Okay. Next one, did I do anything different on this one? Well, unfortunately, let's see what I did. I moved the H and the OH, but I also moved the bottom two. So I did a double flip. So by doing a double flip, basically, guys, if you just rotate this around as a whole thing, it will look exactly like this again. So this is a definition of the same. You can only change two. You can't change four. Or you can only change one group. You can't change two groups around the chiral carbon. So yes, these are chiral, but you can't change both of them. And if you're like, what did I change? Again, the OH was coming at me, now it's going away. This is a methyl, this is an ethyl, now the ethyl's here and the methyl's there. So I flipped this and I flipped this to get to this now. All right, what changed here? First, do I have 4 different things? Yes, I do. So what did I change now? It appears that the H and the Br changed there. So these two switched. Oh, those are only 2. So it's an enantiomer. Three more. Are these enantiomers, or are they the same? Well, right away, these aren't chiral. Reason why? There's 2 Fs. So the minute that there's not 4, I can place them on top of each other. And you can make a model and you can see it immediately. So no matter what I do, I can just flip this around and this is exactly the same as that. So again, I have to have 4 different components around my carbon. Different. So I see 4 different ones. So these are chiral carbon. So I have a chance. There's a uniqueness there. So now what changed? Well, this one's funky. I changed the Cl, the CH3, and the H. That's still just 2 components. Right? Or did, oh my gosh, I didn't see it. I also changed the Cl and the Br. So if you change both, it's like putting it back to the start again. So that is the same. Which leads us into the hardest problem on this page. What's happening here? The problem is with this is that these 2 aren't in the same orientation, let's say. So what I want to do, guys, flip this. So like it's flat, now I'm going to flip this, so this is going to go up, so like the Br is going to come at me and go over. So the H and the F are still the same, apologize. Now by flipping it, the Cl is coming at me and the Br is now going away from me. So think of it like you're flipping your hand from the back of your hand to the front of your hand. Like you're looking at it like that. So because of that, it looks to me like these 2 flipped. So because of that, we're good to go. So this is what I want. I want the same point of view. Because of that, I only changed one thing. It's an enantiomer. We're going to skip this for now, this section. All right, so at this point, what I'd like you to do is you need to start working on stereochemistry number 1 and seeing if you can identify just with an asterisk or not, whether or not it is chiral or achiral. Let's take a look at stereochemistry 1. Pause this if not everybody has this out yet, and I just want to show you what we're doing with this. So the point of this for stereo 1 is that we are just placing an asterisk on any carbons that are chiral carbons. So usually, guys, it's in the middle. Like you're not going on the outside because I have 3 H's right here. I have 2 H's right here. This is not even a carbon. 2 H's, 3 H's. Not going to work. So I'm really focusing on this C. So if I look at this, it's a little pixelated here, but I have a carbon here, and then I have an H, a methyl, a nitrogen, and an oxygen. That's 4 different components. So this is chiral. Okay. And I can keep going through this. I'm going to go down here, though. So here, check this one out. I have my carbon right here. I have a component here. I have an H here. I have this cyclopentane here. And I have another cyclopentane here. So because these are the same, this is achiral. Okay. So to go off of that, I look at this one. I have a very similar one. I have this component here, a cyclopentane here, and a cyclopentene, because I have a double bond. So that is different. So I put a little asterisk, and I say that that is chiral. And that is how I'd like you to work on this worksheet. Should go pretty quick. We'll talk more about stereochemistry on our next part of our chapter.